Welcome, trainees and engineering students. I am absolutely thrilled to have you here today for this explainer. If you're stepping onto a massive modern vessel, you really need to understand how we keep the whole thing from literally dissolving right out from under us. So today, we're focusing our lens on an incredible piece of technology, the Impressed Current Cathodic Protection System, or ICCP, designed by KC Ltd. Specifically, we'll be looking at the exact technical specifications and engineering blueprints from massive 57,300 deadweight ton bulk carrier. We're going to break down exactly how this system works, how it's built, and how you, as future engineers, will operate and troubleshoot it. Okay, let's dive straight into this. Here is our structured map for understanding how we protect a multi-million-dollar vessel. 1. The anti-corrosion mission. 2. System specifications. 3. Core components. 4. Automatic operation. And 5. Troubleshooting and maintenance. All right, part 1, the anti-corrosion mission. Now, the ocean is basically a giant, highly hostile environment for steel. The absolute second a 58,000-ton bulk carrier hits saltwater, this relentless electrochemical assault begins. And to fight it, we have to grasp the sheer scale of the battlefield. We're dealing with a total wetted surface area, meaning the part of the ship constantly submerged in corrosive seawater, of 9,500 square meters, just for the hull. I mean, compare that massive slice to the rudder at 110 square meters and the propeller at just 30 square meters. The sheer volume of metal exposed to the elements is staggering. Protecting 9,500 square meters of steel, that requires a serious electrical counteroffensive. To mount that counteroffensive, we need raw power, based on an applied current density of 30 milliamps per square meter for the hull and rudder, and a much higher 600 milliamps for the propeller. The engineering math tells us we strictly need 306.3 amps of continuous current. But in marine engineering, we don't just scrape by with the minimums, right? The KC Ltd system robustly provides a maximum output of 350 amps. This built-in buffer is there to guarantee total, unwavering protection, even when dealing with the harshest varying salinities in vessel speeds. Moving right along to Section 2, Core Components. Now, what's really interesting about this is how we physically manage that massive 350 amps of protection. It comes down to a perfect contrast between the two frontline soldiers in our anti-corrosion war, the muscle and the senses. On the left, we've got the 175 amp circular anode assembly. Made of mixed metal oxide on titanium, these things are incredibly robust. This is the muscle. It's physically pushing that protective current into the water. Then, on the right, we have the high-purity zinc reference electrode cell. This is the sensory organ of the ship. It just sits there quietly, taking no action other than precisely, continuously measuring the electrical potential of the hull. But as you can guess, muscle and senses are totally useless without a brain to coordinate them. Enter the Combined Power Supply Unit, or PSU, taking in a standard AC 440-volt power feed directly from the ship's generators. This sophisticated unit converts it and pushes out a maximum of 350 amps at 24 volts DC. It also features a touchscreen LCD panel on the front, giving the engineering crew instant access to reference cell potentials, output current, voltage, and all alarm statuses. Simply put, this cabinet is where all the decision-making happens. Which brings us to Section 3, Automatic Operation. So now that we know the key players, let's look at the choreography of how they form a dynamic shield. The beauty of this ICCP system is that it operates as a completely automatic, ceaseless feedback loop once the ship is in the water. Step 1. Those zinc reference electrodes we just talked about are constantly tasting the water, measuring the exact electrochemical potential of the hull. Step 2. That sensory data is transferred instantly back to the intelligent PSU. And Step 3. The PSU analyzes the data, calculates exactly how much protection the hull needs at that very millisecond, and commands the anodes to generate the absolute optimum protective current. It's an amazing system that never sleeps, constantly adjusting to temperature, speed, and water conditions. Of course, to make this feedback loop effective, placement is literally everything. If you follow the lines out from our central 350 amp PSU, you'll see this system divides its power symmetrically. We have one 175 amp node placed on the port side and another 175 amp node on the starboard side, mirrored by port and starboard reference cells. Distributing the hardware like this ensures our protective electrical field wraps evenly around that entire 9,500 square meter hull. So the crucial point here, and you'll see this strict rule right in the manufacturer's engineering notes, is that you must maintain a minimum distance of 6,000 millimeters. That's 6 full meters between the edge of an anode and the reference cell. Why? Well, if the senses are too close to the muscle, the reference cell is just going to measure the massive current blasting out of the anode rather than the actual protected state of the wider hull. Accurate sensor readings rely entirely on this vital spacing. We also can't forget our moving parts. The rudder, even though it's smaller at 110 square meters, is critical. Because it pivots, it's mechanically isolated from the main hull by bearings and lubricants, which totally disrupt electrical conductivity. To fix this, we use a 70 square millimeter rudder stock bonding cable. By securely cramping and electrically connecting the rudder stock directly to the hull plate, we ensure the rudder shares the hull's electrical potential. This one tiny, simple cable ensures our 350 amp shield extends completely over the steering gear.
All right, finally, Section 4, Troubleshooting and Maintenance. For you trainees, this is where the rubber meets the road. Hardware installation is the shipyard's job, but keeping it running for a 5-year voyage cycle, that's on you. Thankfully, the Intelligent PSU is designed to make your life easier by explicitly telling you when something goes wrong. You need to monitor for 4 specific alarm statuses. First, over or under protection tells you the hull isn't sitting in the safe potential zone, meaning there could be a massive shift in water salinity or a sensor failure. An anode fault means the physical hardware pushing the current is compromised or disconnected. A PCB fault points to an internal logic board issue in the brain itself. And a power fail means, you guessed it, you've lost that vital 440-volt supply.
Let's move on and see how this builds, because identifying the alarm on the LCD is really only step 1. Next, we have to look at your actual onboard inventory. When an alarm triggers, especially a power or anode fault, your first line of defense is often a simple fuse replacement. The shipyard provisions a very specific spare storage box for exactly this reason. For a 5-year operational cycle, you're equipped with 5 extra 175 amp anode fuses, 5 extra 50 amp main fuses, and 5 extra 1 amp transformer control fuses. Your ability to clear an alarm and restore that protective shield relies entirely on maintaining organized, accessible log sheets and ensuring these tiny but mighty spare parts are always accounted for. I want to leave you with this provocative final thought as we wrap up this explainer. What happens to the immense 9,500 square meter hull of a 58,000-ton bulk carrier if just one single 50-amp main fuse blows, and the engineering crew realizes they've failed to order spares? Well, the system shuts down, the automatic shield drops, and the ocean immediately begins aggressively eating away at a multi-million-dollar asset. That is the true weight of the responsibility you carry when maintaining an ICCP system. It's a fascinating blend of heavy electrical engineering and precise chemistry, and understanding it is absolutely crucial for any modern seafarer. Keep learning, keep your logs accurate, and I'll catch you in the next one.